Thank you very much for the invitation, and it's very lovely to come to London because it's quite a long way and I don't get that opportunity a lot, so I'm very pleased to be here. So my main talk is to discuss the different models of flow and whether the assumptions that we make are viable, because I think I'm following on a lot from what Professor Dawley was saying, that do we really need to resolve every piece of physics? Okay, so if we do ask ourselves that question of how do we resolve all the physics, we may go back in time and explore the history. And in one of the early papers, 1995, by Kehani, you can see that the model has been truncated, or I guess the resolution of the scan at the time was cut off at halfway. And you see that only 80,000 cells were modelled. Also, it was just a simple momentum problem and no advection was included. Later on, Horschler, 450,000, but only a single chamber, so a unilateral model. But one thing we can take from here is that they've actually used structured mesh, which is something that a lot of CFD people now, or it's pretty much very difficult and almost impossible to apply to today's nasal cavities. And my own work in 2012, we combined the nasal cavity all the way to the trachea, and we pushed our computing limits to 11 million cells at the time. And more recently, Dr. Kelmet, and his supercomputers are at 44 million. Okay, so if we just have a look at that graph, of course we can see there's an upward trend, typically correlating with the computing power that's available. So I did with my students some painstaking review of a lot of papers and tried to extract the number of cells that were reported in the paper. So here are dot points of the reported mesh cells published in which year. So you see there's an upward trend. So I guess from this we can take that in time, new submodels developed, and with computational power, we may be able to resolve a certain amount of physics that was sufficient to be performed on maybe your mobile phone. Okay, so the main three assumptions I will just look at for this talk is that we most of the time assume that our model is a smooth wall, but we know that there's mucus and wet surface. And possibly, I believe that that requires a little bit of further investigation for this, because at that boundary, we know that it's no longer a stationary boundary, and perhaps it's a wet surface that's slightly moving, and so your boundary layer there would be slightly different. In your nostrils, we assume there's no hair, but of course there is. Anecdotally, I've heard that there is pressure drop, and particles that are inhaled are typically filtered out. So some results have shown that downstream in the nasal cavity, the airflow recovers and there is no significant difference. So is the additional computational effort, is that effective in yielding the significant improvements in the model? The other assumption we have is the rigid wall, and I think this is the most important assumption, or the most significant assumption that's applied. Because of the flexibility in the surfaces of the walls, it's prone to collapse in certain regions. So there was a few papers already. Mead Hunter, Australian guy, so I know his work, was to do with the lungs, and the lungs were dynamically moving. And more recently, I read, I think, Professor Dawley's student using a dynamic mesh based on MRI to move the walls. And later on, I won't talk about the heat and mass transfer because it's a discussion in another topic. But that's also another assumption, and so we assume that it's isothermal and no mass transfer. Okay, so if we just take those assumptions and say, okay, we have a smooth wall, a smooth vestibule and rigid walls, then I'll talk about the three models modelling issues, sorry. Is the flow steady? Or can the flow be seen as steady? Or is it unsteady? Is the flow laminar or is it turbulent? And then I'll talk about a few computational models of the flow. Clearly, breathing and respiration is cyclic. And if we look at a few of the papers in the literature, we see that there's large variations between people. So you may get inhalation profile from a smoker, an elderly person, a young person, and they will be vastly different. And so when we consider an unsteady profile and then we look at the sine wave, we think, initially we would think, oh, that's quite simplistic, but it actually will be a really good tool because that could serve as the benchmark because of everyone else's variation, and then we can move that back and say, okay, based on the typical sine wave, this is what X person is breathing like. Okay, so breathing is clearly cyclic, but, which I want to come back to. So if we want to talk about steady solution and what it represents. I thought that, although this is a very engineering topic, which I brought along from one of the courses I teach, if I show you this, I feel that it may be able to explain what a steady solution, that if a CFD's paper is reported and said this is a steady solution, what it actually represents. So this example is a flow moving over a cylinder, and with sufficient momentum in the flow field, there's some flow separation, and then which leads to these vortices moving at the back and oscillating. And clearly when it oscillates, it moves up and down. And so it's not steady. But if we take snapshots of it over time and then overlay it onto each other, so this is the time step 0.7, 0.8, 0.9, and we do that for a long period of time so that we're stepping towards a steady solution. Then that is the solution that's provided by steady state CFD models. And then if we get the boundary of that layer where it's oscillating, then the results will show this smeared pattern, which is essentially an average. It's trying to average the unsteady solution into one image. So you get one image of a steady solution to represent an unsteady solution. So if your flow behaviour or flow physics in what you're looking at is unsteady, then it's something that you need to consider when you're interpreting those results. And so if we look at the work out there, and a lot of it is steady, then how is that represented? And so here is our sine wave, and it's very, very averaged. So let's assume that the breathing cycle is 4 seconds. The tidal volume is half a litre, 500 mils. So if you take the average of that, of the 500 mils, then we're considering that flow as a steady state flow for 2 seconds. So that equates to an average of 15 litres per minute. And per cycle, which is just that one wave there, it's 7.5 litres per minute. And the peak velocity, or peak flow rate, sorry, is 23.7 litres per minute. And when we do our CFD simulations, and because I try to find this in the methodology, is that it should be going for a few waves. Because if it's starting from zero, then you need to remove those startup effects, and the fourth cycle should be the cycle that's being analysed. I'm putting this in here because this has very strong significance in the modelling issues. Okay, so we'll come back to that, but to answer the question, is the flow steady or unsteady, we visit some literature. So in 1993, Han presented some experimental measurements and calculated the Struhl number, and Professor Dawley did as well. And the Struhl number represents the relationship between whether it's steady or unsteady, and any value that is less than 1 is seen to be in the steady regime. And also the Wormsley number is also used, and despite the fact that that is above 1, a lot of people will still take the fact that the Struhl number dominates the flow. And so based on this, these two numbers, then people are satisfied by claiming that the flow can be modelled as a steady flow or quasi-steady. And Professor Doolittle again, in his paper, that yes, it can be used as steady, but we must be aware that its use for cumulative processes can be fraught with errors. And that's because of your acceleration and deceleration and the hysteresis of the flow behaviour. So we can look at further literature, and you look at the top and the bottom, the top being the unsteady simulation, the bottom image is the steady. It's quite difficult to see from first glance the difference. And you may ask yourself, well, is there any difference? And because of that, I took some time to find and show you where they are. And again, this comes back to our question, do we really need to resolve every detail in physics? Is steady flow to provide gross flow features sufficient for our application? In terms of particle tracking and deposition, there's a little bit of difference as well, reported in 2016 paper. Okay, so having said this, why do we need to model steady flows at all? I did some quick calculations. A 4 million cell model uses up 300 megabytes, and using the flow conditions at 15 litres per minute, I worked out it's on average 3.18 metres per second. For that to traverse the nostril to the pharynx of 0.1 metres, the time to traverse that nasal cavity is 0.03 seconds. Okay, there's a lot of numbers. Perhaps I'll leave you to look at it later through the videos, but I work out that, okay, the number of simulation time steps you need is 52,000 steps, and we're assuming you can do 40 iterations per time step. And so based on a $3,000 desktop computer, it may take you 74 days. But that's very crude, and there's strategies to implement to reduce that simulation time. Just a quick comparison with the steady state, we see that, okay, a steady state you only have to do 1 through simulation, and you're looking at three hours. Okay, so what I was trying to say is that yes, breathing is clearly cyclic, but steady flows can be useful if you can accept some of the limitations because it's fast, it's easy to understand, and it's computationally efficient. It allows substantial interrogation of the geometry and cause and effect relationships, because when you're looking at unsteady flows, there's so much data, and you just, unless you have a clear idea of what you're looking for, it's quite challenging. All right, sorry about that. Okay, so the other question we ask ourselves is it laminar or turbulent? If I take a point in one of the slices in the geometry and track its velocity over time, then we can take a time average of those oscillations and get an average velocity. And then we try and find the difference between the average velocity and the we call it the dispersion, the velocity dispersion, and then we can average that, and that becomes our intensity, our turbulence intensity. But we should be aware that an unsteady flow can also be laminar, and so just because we see oscillations and recirculations in flow, that such flows can remain laminar but have a repeating and unsteady and oscillating flow profile. Okay, so this is one of the more controversial issues, whether the flow is laminar or turbulent. And before we make the decision, or I give you my opinion, then let's have a look at a very fundamental fluid dynamics case. And the nasal cavity is essentially internal flow, which we define internal flow as a wall-bounded flow, and because of that, the surfaces that bound the flow have a significant effect on the flow field. So if we have a look at these two profiles on the inside, we have a laminar flow, which is the one that comes out further in the pipe there, and then we have a turbulent flow profile, which is a little bit more blunt, and the profile is a bit more. The profile near the wall is a lot closer. And we also consider the Reynolds number, which I'll talk about later. Okay, so in Hahn's experiment, he did 3 flow rates given there. And we see that he looked at it in 2 different planes. And if we recall from those profiles, we see that at the high flow rates of 1,100 milliliters per second, those profiles are very blunt. And then if you shift over to the 180 milliliters per second, they're a little bit more parabolic. And so it comes down to, and then we can conclude, or he concluded that yes, the lower flow rate was laminar and the higher flow rates were turbulent. So his work, a single geometry was used, it was relatively smooth, a single chamber was used, and it was truncated at the back. Now, just recently, Lee, 2017, used the same model around LES, DNS, and a multitude of turbulence models, and confirmed that yes, indeed, 180 milliliters per second was laminar, and they found that the standard K omega provided a better performance, although previously the standard that everyone was using was the SST K omega. Professor Dawley's paper also mentions that it's predominantly laminar, at least to the middle turbulent. And further back, Cockcroft in 1979 says that it's dominated by turbulent regimes, although laminar flow may also exist. Okay, the work by Churchill really tried to investigate what geometry effects would then influence the flow dynamics. Now, the turbulence that project into the nasal cavity, there was 2 groups saying that it induced turbulence. However, those turbulence appeared to laminate the flow based on Churchill's work. And if we have a look here, we can see that as these turbulence project into the nasal cavity, it reduces the airway space, so the walls of the nasal cavity are closer, and when they're closer, then those wall effects, which we have, or which we consider as viscous effects in engineering, they tend to oppose the fluid motion and tend to laminate the flow. So from that, we would conclude that the projection of turbulence into the nasal cavity tend to laminate the flow. So the nasal orientation was also discussed, and his work said that it was moderately correlated with flow dynamics, but Professor C's work said that it actually had a dramatic effect on the ventilation. Okay, so the conclusion on this is there's a lot of different ideas, and I think the issue is that there's the different geometries being used, and so a consensus is very difficult. So I'm going to take this image and say that I'm sitting on the fence like the squirrel. But generally speaking, less than 15 litres per minute is likely to be laminar dominant, if we can generally speak, and more than 20 litres per minute is likely to be turbulent dominant. Okay, so if we are to take laminar flow, it is okay if the sufficient low flow rates are taken, and we accept that there's a viscous and thermal diffusion caused by the turbulence is not being accounted for. And we should also really think about how prominent are the effects of that geometry on my flow field. All right, I might leave the turbulence models because I think I'm going over time, but I'll leave the slides, maybe I'll make it accessible. It's more about the flow characteristics that help us define whether or which turbulence models are best to use. I will skip it all, but I wanted to just quickly talk about the Spallart-Almaris model, because it's a one equation model and it's not prominent in the work, in the literature, because it's always seen as the most simple model, and so that it therefore doesn't account for as many physics. But when we look at what it's good for, which is wall-bounded flows, flows with mild separation and recirculation, and previously designed for low Reynolds numbers and for unstructured codes, then it has very good potential. So it's something that we should consider. And the rest I will skip, sorry. Okay, so thank you, because I've gone a little bit over time.